There are symbols so familiar that we have almost ceased to see them. We use them every day. To tell the time, to pay a bill, to measure a distance, to remember a date. Among them all, there is one that is particularly strange. A small, closed figure, an almost empty stroke. 0. Today, we write it without a second thought. But for much of human history, the idea of representing nothingness with a number would have been baffling, even absurd. How can you count what does not exist? And yet, without this written nothingness, our way of representing numbers would be impossible.
This is the story of an invention that was not the work of a single person or a single civilization. It is the story of marks engraved on bones, wedges pressed into clay, drawings carved in stone, rods arranged on a table, pebbles moved across lines in the sand, and signs patiently copied from one manuscript to another. It is also a story of merchants, priests, astronomers, scribes and travellers, a story that crossed deserts, ports and imperial roads. The long journey that transformed a few counting marks into a language capable of expressing any imaginable number.
In this episode of Histarmat, we will follow that journey, from the very first traces of the act of counting to the Hindu-Arabic system we use today, and we shall see how a seemingly simple idea changed the history of human thought forever, that the value of a mark can depend entirely on its position. We do not know exactly when this story began. At some remote moment, when humans still lived surrounded by daily threats and observed the world with a mixture of fear, necessity, and wonder, someone deliberately left a mark. Perhaps it was an incision on a branch, a line drawn in the sand, a notch carved into a bone. Long before alphabets existed, humans were already covering the walls of certain caves with pigments. Over 40,000 years ago, in the cave of El Castillo in Spain, people placed their hands against the rock and blew colour around them. They left a presence, a sign, a memory. A mark can mean many things. It can warn of danger, it can point the way, it can record an event. But it can also register a quantity. One sheep, another sheep, a third. At first, counting did not require understanding the number as an abstraction. A shepherd could notice an animal was missing without knowing exactly how many made up the flock. Recognizing an absence is different from enumerating a collection. The true intellectual leap consisted of establishing a correspondence, one mark for each object, one notch for each animal, one stone for each measure of grain. This gesture seems humble, but it already contains an immense idea. Things can disappear. Sheep can wander off. Sacks of grain can be stored in another building. Yet their quantities can survive, translated into signs. The material world begins to duplicate itself in a world of marks. In Mesopotamia, towards the end of the 4th millennium BCE, we find some of the oldest surviving written records. They are not epic poems or tales of heroes. They are accounts. Fragments of clay tablets from the city of Uruk preserve calculations related to the surface area of fields. Written mathematics predates literature in many cases. Before recording grand stories, the first cities needed to record lands, animals, tributes, and harvests. The emergence of numerals cannot be separated from the birth of cities.
Large agricultural settlements demanded calendars, land registries, taxes, storehouses, and trade networks. Temples were far more than places of worship. They could function as observatories, archives, administrative centres, and treasuries. To govern a city, one had to count. To count accurately, one had to record. And to record, it was necessary to invent signs that remained when individual memory was no longer enough. On the plain situated between the Tigris and the Euphrates emerged one of the most ingenious numerical systems of antiquity. We call it Babylonian, although its history also encompasses Sumerian and Akkadian traditions. Its scribes did not draw numbers with ink. They pressed a stylus into wet clay. The instrument left small wedge-shaped impressions. A vertical wedge could represent a unit. Another wedge, oriented differently, could represent a 10. With just 2 kinds of marks, carefully grouped, scribes could represent quantities smaller than 60. But the system held a greater surprise. Upon reaching 60, the very same mark acquired a new value depending on its position. A wedge could mean 1 unit, but shifted to the left, it could mean 60 units. And shifted 1 position further, 60 times 60. The essential idea was extraordinarily powerful. The same figure could mean different things depending on the place it occupied. We do something similar every time we write a number. In the quantity 234, the first digit does not simply mean 2. It means 2 hundreds. The second represents 3 tens. The third, 4 units. Position modifies value. The Babylonians had already discovered this idea thousands of years earlier. Only their system was not organised in groups of 10, but in groups of 60. We still preserve traces of that choice every time we divide an hour into 60 minutes or a minute into 60 seconds.
But there was a problem. What happened when a certain position contained no quantity? For centuries, scribes simply left an empty space. That void functioned as a silent pause. The reader had to interpret, according to the context, whether the gap corresponded to 1 empty position or more than 1. Without visible borders, 1 gap could easily be confused with another. Absence needed a mark.
At some point, roughly between the 7th and 3rd centuries BCE, a special sign appeared to indicate an empty position. It was a primitive form of 0. But we must be careful. It was not yet a number that could be added, subtracted, or considered a quantity in its own right. It was a placeholder, a traffic signal within numerical writing. It indicated that there were no units of a certain rank there. Nothingness had obtained a mark. It had not yet obtained full mathematical citizenship. While the scribes of Mesopotamia pressed wedges into tablets, the Egyptians developed a different strategy. Their system was decimal, but not positional. Each power of 10 had its own hieroglyph. A unit was represented by a small vertical stroke, 10 units by a figure resembling a curved rope, 100 by a spiral, perhaps a coiled rope, 1,000 by a lotus flower, 10,000 by a raised finger, 100,000 by a figure that some interpret as a tadpole, a fish, or a frog, and 1,000,000 by a character with raised arms, as if the sheer magnitude of the quantity had left him in awe. To write 3,000, the lotus flower was repeated 3 times. To write 600, the spiral corresponding to hundreds was repeated 6 times. The system was additive.
The total quantity emerged from gathering the necessary images. There was no need for a zero. If there were no tens, no curved rope was drawn. If there were no hundreds, the spiral was omitted. It was a clear, expressive, and perfectly functional system, but it could become laborious as quantities grew larger.
Here emerges a tension that will accompany our entire story. A system can be understandable and yet uneconomical. It can be adequate for recording a quantity, but prove cumbersome for calculating with it. The history of numerals is not solely the history of how to write numbers. It is also the history of how to make them manageable for the mind.
Other cultures chose to turn letters into numbers. The Hebrew alphabet assigned numerical values to its characters. Some letters represented units, others tens, others hundreds. The system allowed quantities to be written relatively compactly, but it required memorizing numerous values. Furthermore, letters were not simple neutral marks. They retained linguistic and religious associations. The number 15, for example, was not written using the combination that would have formed the first letters of the name of God. Another equivalent sum was used instead.
A numeral never lives completely isolated from the culture that uses it. It can evoke words, sounds, beliefs, or traditions. Even when its function seems purely practical, a symbol drags a history along with it. The Greeks used more than one system. At an early stage, they resorted to acrophonic signs, marks derived from the initial letters of the words used to name certain quantities. Later, a sequential alphabetic system prevailed, similar in spirit to the Hebrew one. The first letters represented units, other letters tens, others hundreds. The result was compact for certain quantities, but awkward when working with large numbers.
This choice is particularly striking. The Greeks were aware of Babylonian mathematics. Their greatest thinkers reflected on geometry, proof, irrational numbers, and the logical structure of knowledge. Yet they did not generally adopt a positional system that would facilitate written calculations. Perhaps because many operations could be performed with abacuses and counting boards. Perhaps because their mathematical interests were oriented in other directions. Genius in one area does not guarantee the invention of all possible tools.
This distinction is important. A civilization could possess an inflexible numerical writing system and at the same time perform complex calculations with auxiliary instruments. For centuries, writing a quantity and operating with it were partially different activities. The counting board allowed stones to be moved from one line to another. One line corresponded to units, another to tens, another to hundreds. An empty column alone could express the absence of a certain magnitude. The Roman system inherited another variant of this tradition. It combined signs using rules of addition and, in certain cases, subtraction. We still use it on clocks, monuments, and ceremonial dates. But its decorative elegance should not mislead us. For performing extensive calculations, it was far less convenient than our current system. The Romans could calculate, of course. They did so with boards and abacuses. The difficulty lay not in the intellectual capacity of those who used them. It lay in the available writing. So far, we have traversed regions connected in one way or another by migrations, conquests, and trade routes. But on the other side of the ocean, without contact with Eurasia for tens of thousands of years, surprisingly similar solutions emerged. Mayan numerals offer one of the most fascinating examples.
The Mayan system used dots and bars. A dot represented 1 unit, a bar represented 5 units.
Quantities were organized vertically, in levels. Each level acquired a different value according to its height. Broadly speaking, it was a system based on groupings of 20, although its calendrical use introduced a peculiarity in one of the levels. Once again, the great idea appears. Position transforms value. But positional writing inevitably stumbles upon the same problem. What happens if one of those levels contains no quantity? To write 20, for instance, one unit had to be indicated on the upper level and no units on the lower one. If the lower level were left simply empty, the writing could be ambiguous. The Mayans designed a symbol for that void, a figure resembling a shell. Its function was that of a placeholder. The parallel with other cultures is extraordinary. With no historical contact with Babylon, China, or India, the Mayans found an answer to the same conceptual problem. When value depends on position, even absence needs to be made visible. No numerical system evolves in a vacuum. Between China, India, Persia, and the Mediterranean stretched a network of land and sea routes that we tend to summarize under a single name, the Silk Road. It was not a single highway. It was a constellation of trails, stopovers, ports, and trade links. Along them travelled silk, perfumes, spices, precious stones, metals, carpets, and wines. But alongside the goods travelled methods, tales, religions, diseases, and mathematical knowledge. Trade demands comparison. How much silk is equivalent to a certain amount of silver? What is the weight of a commodity? How is a local measurement converted into one used in a distant city? Wherever two merchants meet, two ways of counting meet as well. The routes of exchange were, inevitably, routes of mathematical translation. In China, the oldest numerical records we know of date back to the Shang dynasty. Thousands of bones and fragments of tortoise shells preserve inscriptions linked to sacrifices, battles, hunts, and tributes. Quantities of captured animals, defeated enemies, and offerings made appear there. Once again, counting is a way of managing memory. By the beginning of the Han dynasty, a decimal system of numerical characters was already established, very close in its logic to the one still used in China. The writing explicitly named the ranks: 2 tens of thousands, 6 thousands, 9 hundreds, 9 tens, 9 units. If there were no hundreds or tens, those words were simply omitted. It was not necessary to write a 0 as a placeholder. The verbal and graphic structure itself made it clear which ranks were absent. However, for performing daily calculations, another tool was used: counting rods. They could be made of bamboo or bone. They were arranged on a table as if they were small sticks. Their vertical and horizontal orientations represented quantities from 1 to 9, and their position on the board indicated whether they were units, tens, hundreds, or higher ranks. In this system, a position without rods functioned as an empty space. But Chinese calculators developed an ingenious solution to reduce ambiguities. They alternated the orientation of the rods across the different ranks: vertical, horizontal, vertical, horizontal. Thanks to this visual rhythm, one could distinguish whether there was a single empty position or more than one between two figures. Absence did not yet have a sign of its own, but it was caught in the alternation of the neighbouring marks. The rods were far more than a counting instrument. They allowed for addition, subtraction, multiplication, division, and even working with positive and negative quantities. The celebrated treatise known as the 9 Chapters on the Mathematical Art presupposes mastery of these procedures. Unlike the Greek tradition, centered on deductive proofs, Chinese mathematics developed persuasion through examples, analogies, and algorithms with great refinement. It was not an inferior mathematics, it was another way of organizing knowledge.
Some historians have pointed out the remarkable conceptual similarity between the Chinese rods and the system we later associate with India. Both are decimal, both use positions, both allow for the development of very similar calculation procedures. Did these ideas travel from China to India? It is possible. Trade routes offered pathways for transmission, but the documentation does not allow us to reconstruct a continuous, certain line. In the history of symbols, the silences of the archive are just as important as the evidence that has survived.
In India, we find the decisive step towards our current system, but we must avoid an overly simple narrative. Numerals did not suddenly appear with the forms we know today, nor did they emerge as a perfectly finished invention. Their contours changed over centuries. Some rotated, others were stylized. Many went through intermediate stages that have been lost forever. One of the fundamental precedents is the Brahmi system. Some of its simplest forms vaguely recall certain modern numerals, but its logic was different. It was not yet a fully positional system. There were distinct signs for units, for tens, for hundreds, and for other larger quantities. Writing 220 required combining the specific symbol for 200 with the specific symbol for 20. Position did not do all the work. The graphic genealogies of our numerals are tempting. We would like to observe a clean evolution, an ancient form that slowly modifies until it becomes each of our digits. But the real history is more fragmentary. The mediums change. Stone demands one gesture. A stylus on clay demands another. Ink on parchment favours swifter strokes. Scribes copy, simplify, distort, and sometimes misinterpret. Writing is also made up of accidents. It is possible to imagine how a succession of independent lines ends up becoming a single continuous stroke to save time. But we must distinguish a plausible explanation from historical certainty. Many stages remain in the shadows. We know that the forms evolved. We do not always know where, when, or by whose hand. Over time, a decimal system was consolidated in India, in which the same 9 figures could be reused in different positions. A figure could represent units, in another position, tens, further on, hundreds. Some manuscripts, such as the famous Bakshali manuscript, preserved fragmentarily on birch bark, offer important evidence. Its dating has been the subject of debate, but the essential point remains. In the Indian tradition, we find a positional writing increasingly closer to our own. The 9 figures resolved almost everything. Almost. To write any quantity using positions, it was also necessary to indicate that a position was empty. The language needed to name the absence. In Sanskrit, the word used was shunya, empty. The year 628, the mathematician and astronomer Brahmagupta wrote a work known as The Correctly Established Doctrine of Brahma. There we find one of the great moments in this story. Brahmagupta used a small, dark dot to represent 0, and he went beyond the simple placeholder. he formulated rules for operating with this new entity. 0 began to behave like a number.
Brahmagupta described positive quantities as fortunes and negative ones as debts. If a quantity is subtracted from itself, nothing remains. That nothingness has a place in the system. It is not solely a gap between other digits, it is the result of an operation, a quantity that expresses the absence of quantity. The conceptual step is profound, because counting 2 objects seems natural, but counting no objects requires transforming absence into a manipulable idea. For thousands of years, different cultures had developed tools to indicate empty spaces. The Babylonians had used a placeholder. The Mayans had created their shell-like figure. Chinese calculators had resorted to spaces recognizable by the alternation of rods. But in India, the void acquired a new force. It was not solely a pause within the writing, it was a number. To understand why this revolution took time to take hold, we must remember something essential. People could calculate long before they possessed convenient numerical writing. 100 sheep are difficult to count if they are moving across a field. 100 stones, on the other hand, can be organized into piles. 10 piles of 10 stones are easier to control than 100 scattered stones. From this intuition, counting boards were born. Lines were drawn on a board covered with dust or sand. One corresponded to units, another to tens, another to hundreds. Pebbles could be moved, removed, and regrouped. An empty column indicated that there were no units of a certain rank. There was no need to draw a 0. The board physically displayed the absence. The Roman abacus applied the same logic, using small metal balls sliding in grooves. To operate, the merchant did not need to write a long sequence of Roman numerals. He moved counters. The positional idea already existed within the instrument. What was needed was to free it from the board and convert it into a portable writing, a writing that could travel on a page. The Indian figures began to travel westward. In the Islamic world, they found an extraordinarily fertile intellectual environment. In Baghdad, during the Abbasid Caliphate, the translation of works from Greece, Persia, and India was encouraged. The so-called House of Wisdom became a centre for the study, preservation, and circulation of knowledge. Muhammad ibn Musa Al-Khwarizmi worked there. His name would leave an unexpected mark on modern languages. From the Latinization of his name comes our word algorithm, and from the title of another of his treatises comes the word algebra. But in this story, we are particularly interested in his work dedicated to calculation with Indian numerals. We do not know for certain what Al-Khwarizmi looked like. The portrait that usually accompanies his name is a later creation. But we do know the importance of his task. Around the 9th century, he wrote a treatise on arithmetic based on the Indian system. The original Arabic work has not survived. His ideas reached Europe through later Latin translations. The Indian void, shunya, found the word cipher in Arabic. From there come terms that are commonplace to us today, cipher and 0. It is a small archaeology of language. Every time we speak of a cipher, the remote memory of that nothingness turned into a sign still resonates. We must not imagine a triumphant and linear march. The new figures circulated along diverse routes. They reached scholars, monasteries, ports, and translation centres. They changed shape according to the region. In some places, they coexisted for centuries with alphabetic numerals, written words, and abacuses. A good idea can be known long before it is adopted. In Western Europe, we find numerals of Indian origin before Fibonacci. An illuminated manuscript written in Spain around the year 976, known as the Codex Vigilanus, preserves an early series of these figures. Their shapes are not identical to ours, but the kinship is recognizable. Shortly after, Gerbert of Aurillac, the future Pope Sylvester II, promoted a calculation board that used small tokens marked with signs similar to the Indian numerals. These tokens were called apices. Each one replaced a set of pebbles within a given column. The advance was significant. A single marked piece could represent several units of the same rank. However, Gerbert's board did not yet exploit the full potential of the new writing. The figures remained tied to an instrument. The absence of a token in a column was enough to indicate the void. The written zero did not seem essential. Europe had received part of the mechanism, but had not yet fully grasped its scope. During the 12th century, various Latin translations helped to spread techniques originating in the Islamic world. Toledo was one of the great centres of this movement. Robert of Chester, John of Seville, and other translators enabled European readers to learn calculation methods associated with the Indian figures. The information was circulating. Everyday practice advanced much more slowly. In the year 1202, a work appeared that was destined to become a milestone. The Liber Abbaci, or Book of Calculation, by Leonardo of Pisa, better known as Fibonacci. His name is often associated with the famous sequence linked to a problem about the reproduction of rabbits, but his historical importance is far broader. Fibonacci was the son of a Pisan official stationed in Buja in North Africa. There he learned the calculation methods used by merchants and masters of the Mediterranean world. He travelled through Egypt, Syria, Greece, and Provence. He compared procedures. He observed different systems, and he became convinced of the practical superiority of the 9 Indian figures, accompanied by the sign that the Arabs called Zephyr. The Liber Abbaci begins by presenting 9 Indian figures. With them, and with the sign of 0, Fibonacci asserts any number can be written. The idea is almost dizzying. A finite repertoire of marks allows for the representation of a potentially infinite collection of quantities. We do not need to invent a new sign every time the number grows. We reuse the same figures. Position does the rest. Fibonacci did not write solely for philosophers or astronomers. His work had a decisive commercial dimension. He taught how to calculate prices, profits, currency conversions, weights and measures. It allowed for operations on paper without constantly relying on the abacus. It was a mathematics for ports, markets and trading houses, a portable intellectual technology. But we must avoid a very widespread simplification. Fibonacci did not single-handedly introduce the Indian numerals into Europe. They were already known before he wrote his book. They circulated in manuscripts, translations, and calculation boards. Some merchants probably used them partially. His merit was different. Fibonacci was an exceptional expositor of knowledge that was already travelling across the Mediterranean. He helped to demonstrate its power and broaden its spread. History rarely depends on a single hero. The Liber Abbaci was a fundamental work, but it was not the only path. Ideas advanced through many channels.
travellers, freed slaves, merchants, rabbis, translators, calculation masters, monastic manuscripts, and urban schools. The revolution of numerals was a collective endeavour. The adoption of the new system was not immediate. In Florence, in the year 1299, an ordinance forbade the use of the new figures in certain financial records. The reason was understandable. A 0 could be transformed into a 6 or a 9 by adding a small line. Written words offered greater security against fraud. There was also a less philosophical and more everyday obstacle. Paper was expensive. Written calculations require crossing out, correcting, and discarding pages. A counting board, on the other hand, could be used time and time again. Technologies do not triumph solely because they are conceptually superior. They must be integrated into concrete habits, economies, and materials. During the 14th and 15th centuries, the so-called Abacus schools of northern Italy played a central role. There, masters taught commercial arithmetic in the vernacular language. They trained merchants and artisans. They explained conversions, proportions, and algebraic problems. Paradoxically, the name of these schools did not necessarily mean that a physical abacus was used. It designated a practical tradition of calculation inspired by the commercial world. An engraving published at the beginning of the 16th century visually summarizes the transition. On one side appears a calculator leaning over a board. On the other, a figure operates using written digits. Between them stands the personification of arithmetic. The image presents almost a competition between two ways of thinking. One relies on movable objects, the other trusts in signs drawn on a surface. The digits continued to change their appearance. Some medieval forms would be baffling to us. The 5 could look like a turned letter H. The 4 did not look much like ours. The signs rotated, curved, and simplified. Only slowly did they converge towards the figures we recognize today. Even in the 16th century, Roman numerals, Indian digits, and numbers written entirely in words could coexist. Over time, the advantages of the system became irresistible. 10 signs were enough to write any number. Operations could be transferred to paper. The rules could be taught, repeated, and disseminated. But complete triumph in European schools and commerce did not arrive immediately. It was necessary to pass through centuries of coexistence, suspicion, and learning. It would be tempting to close this story with a perfectly ordered genealogy. First, Babylon, then China, next India, later Baghdad, finally Europe. But the evidence does not allow us to construct such a sharp line. Ideas may have travelled along routes we are unaware of. They may have developed in a partially independent manner. They may have been transmitted orally long before appearing in a preserved manuscript. Did the Chinese rods influence the Indian system? Did certain numerical forms reach Alexandria through merchants? What manuscripts were lost to dampness, fire, or neglect? We do not have definitive answers to every question. The historian works with fragments, with partial testimonies, with silences. Joseph Mazure dedicates the close of this history to a warning. During the 19th century, some debates on the origin of numerals became entangled with national rivalries, dubious documents, and even forgeries. The desire to attribute a great invention to a specific culture can distort the interpretation of evidence. The history of mathematics demands admiration, but it also demands prudence. A written form can hide centuries of transformations. It may have been copied, rotated, simplified, or corrected. Even when we recognize a resemblance, we must ask ourselves whether it is a proven historical relationship or merely a plausible conjecture. Symbols appear motionless on the page, but their history is full of movement. And so we return to 0. A small figure that can indicate an empty position, but which can also represent a quantity, none. A mark that seems to contain nothing, and yet makes almost everything possible. Thanks to it, we distinguish between 25 and 205, between 7 and 70, between a solitary digit and an immense magnitude. With a repertoire of just 10 signs, we can write any whole number, however large. A figure is reused time and time again. It changes value when it changes place. The system seems so natural that it is hard to imagine humanity could ever live without it. But for millennia, it did. Simplicity, when finally achieved, can obscure the effort required to discover it. Behind every digit we write, there is a silent multitude. Scribes of Mesopotamia leaning over wet clay, Egyptian priests engraving lotuses and spirals, Mayan calculators arranging dots and bars, Chinese masters moving bamboo rods, Indian astronomers reflecting on the void, Arab translators copying manuscripts by the light of a lamp, Mediterranean merchants comparing prices in distant ports. None of them could fully foresee the destiny of their marks. Numerals are tools, but they are also traces. They preserve the memory of how we learned to separate a quantity from the things being counted, of how we discovered that a position can change a value, and of how, in one of the most audacious leaps in human thought, we turned nothingness into something that could be written down, nothingness into a symbol, and the symbol into a gateway to the infinite. This is Histarmat, history, art, and mathematics.